we have Ciro, and Ciro is going to be talking a bit about bitrate evaluation of compressed HDR using SL-HDR1. And because this had HDR in the title, I see you chose Matthew Goldman as your wing person, and you know, against my better judgment, you know, we went with that. So all I can say is good luck, and take it away, Ciro and Matt. We're really glad you guys are here. Thank you.
All right, thank you. This is sort of an evolution of the presentation I had at last VidTrans, and that's something that Mr. Goldman had inspired me to do. I had a talk at VidTrans 2017 about HDR. I talked about stuff like this, and he says, well, I was reporting someone else's findings, and he doubted a little bit, so I went and did my own once I was in a position to do that.
I doubted it a lot.
Yeah, and we'll have a lively discussion about that. A little bit of an introduction about HDR. HDR works by changing the interpretation of the video samples, what the actual luminance level is represented by a video sample. Video encoders are by and large, not completely, but by and large, agnostic to HDR. They just pass that stuff on. There's things you can do to optimize for HDR, but they are by and large agnostic to that. So the objective of this talk is to analyze two ways of transporting HDR over compressed link. We can either do it natively or use SL-HDR1, which I'll describe in a minute. So let's take a quick overview of HDR. The human eye response is nonlinear, so we perceive more detail at the lower luminosities. So you can assign bits to light intensity in this nonlinear fashion, more bits to the lower intensities and the higher intensities to less bit, but to express higher range, pretty much like we did for audio, for voice, long time ago. Same idea. So in the display, this is the EOTF, the electrical to optical transfer function. So the higher lights mean more light. Fundamentally, HDR shows more detail in the bright areas.
Yeah, just one further comment on that one, Ciro, for everybody here. So people get confused, if you just want to flip back for a second.
Sure.
People get confused on HDR. They think just think of HDR as being a wider dynamic range. You see more detail in bright areas, and you actually see more detail in dark areas too. It's and that's really the whole purpose behind it. It really is not about having a brighter screen overall, like if you're in a bright room turning up the ambient light level. It's about being able to experience more like the human vision has, which unfortunately, until HDR came along, television had a rather narrow dynamic range. The really bright areas weren't that much different from the average area in the background. In the dark, a lot of times you couldn't see any detail at all if there was any brightness in the picture.
All right, thank you. So a little note about relative versus absolute luminance levels. In SDR, the luminance is relative, means 100% give me your best shot at a white. For HDR, the basis for that is that the implementations, the SMPTE ST2084 perceptual quantizer. And I got that right, Matt? SMPTE space ST space 2084, right?
You did.
All right, thank you for that.
But I think it's also good to point out that the SMPTE standard has also been standardized as an ITUR recommendation. It's in BT 2100. All
right, thanks. So in PQ, what you code is the absolute value of the luminance. And the light intensity is measured in candelas per square meter, which is also called a nit. A standard TV monitor can do about 100 nits, and HDR can code up to 10,000 nits, which no commercial monitor can do. Although people have demonstrated monitors with 10,000 nits. I don't know if you can buy one today, but they have been demonstrated.
Consumer sets, the high-end ones are probably about 2,000 to 2,500 nits. Again, in the highlighted area, the whole display can't generate enough energy that it would, of course, it wouldn't be Energy Star at all either, right? But yeah, areas of the screen can be as bright as 2,000 and 2,500 in a lot of the LED lit LCD displays today. OLEDs are a little bit lower than that, but on a commercial monitor, the highest I'd seen was about 6,000 nits. I mean, they're getting up there, but they very thick, huge fans on the back, and you get a sunburn by standing in front of the display at the same time. But as technology gets better over time, we will start to see consumer televisions that probably will exceed 3,000 nits. I mean, I don't work for any of the companies, so I can't say that definitively, but that seems to be the direction they're going in. And the thing about OLEDs is they might not be as bright. They might only be 800 to 1,000 nits at the upper end, but they do black levels really, really well. So that's, again, it's about the dynamic range, the difference between the dark areas and the bright areas.
All right. So what happens at the monitor? The monitor may get an HDR signal that it cannot display because it says, give me 5,000 nits and it cannot only 2,000. So you need to create an image that is as close as possible to the original based on what it can actually do. In order to help the monitor to do that, in some HDR standards, metadata is included in the stream. And what's in that metadata? In most HDR standards, metadata describes and what is in the signal. However, in SL-HDR1, metadata contains instructions on how to recover the HDR signal, because SL-HDR1, the base signal is not HDR.
Yeah, this really is an important difference to point out regarding SL-HDR1 between a lot of the other HDR standards that use metadata. Metadata in those standards is descriptive. Think of it the same way for those that are familiar with like active format description, that might say it's a shoot and protect 4x3 within a 16:9 raster or something like that. It tells you what you have. It doesn't tell you what to do. The device that receives the metadata will use this information, of course, to try to get the best picture as it can, but it's a descriptive thing. It's different in SL-HDR1. It's actually prescriptive metadata. It actually tells the receive device how to properly recover the HDR portion of the signal.
Yes. So let's dive a little bit in the details. SL-HDR1 is defined in an ETSI standard. I'm not going to read all the numbers. It was also included in ATSC 341. It's part of ATSC 3.0. The base layer is SDR, and the metadata allows you the mapping for anything between HDR and full HDR. The other HDR standards have an HDR base layer. So Matt said, the other HDR standards is HDR with descriptive metadata, and SL-HDR is an SDR with instructions.
But I do think it's important to point out something here, and I'm not sure how it's going to be used in practice. I did take a look at the attendance list, by the way, which is fantastic for the for VSF. There's like over 100 people on here when I last checked it. Fantastic. Anyway, the SDR isn't an SDR. Well, it can be, but in the case of the examples of the test here, the SDR isn't an SDR that can feed into a backwards compatible set. In other words, you'll see this a little bit later on when Ciro goes through the details, but to be backwards compatible, it's not just about the dynamic range. You also have to do the bit depth, and backwards compatible, we have to be 8 bits. And the color space itself would have to be ITUR BT709, where for Ultra HD, the color space is BT2020, which again is also in BT2100.
All right. So if you want the technical details, the metadata carriage is defined in SMPTE 2108 for the SDI, and in the compressed streams, they are sent as SCI messages. So we get to the core of this talk, which is our objective is to transport the native HDR signal through a compressed link at a given quality, which is measured objectively. This can be done in 2 ways. You just send it. You can directly encode the HDR signal. You obviously need to use 10 bits for the encoder and decoder, and then you just decode it. Or you can use SL-HDR1 to convert the signal to SDR plus metadata, encode it, transport the signal and the metadata, decode and convert back to HDR. So in both cases, you're coming in with HDR, you're coming out with HDR. Now, is there a difference in bit rate? That's the question we're trying to answer to achieve the same quality. Do you need to go higher or lower with SL-HDR1? So here's my test setup. We start on HDR video source, obviously, and that HDR video source gives me a reference signal, which is the basis for my comparison for when I compare quality. I take an AVC or HEVC encoder. We're going to do this both in AVC and HEVC connected to a decoder, and I'll send that to through that path. So encode and decode. I can also do SL-HDR. So this path one that I show is direct HDR. Or I can drop in an SL-HDR encoder and SL-HDR decoder, and then run the path through that. So in the purple side is an SDI signal with SMPTE 2108 metadata, and in the brown part is a compressed signal with SL-HDR1 in the metadata. Also, I can do a bypass the encoder and the decoder, just straight SL-HDR1 without compression as a reference point. And then based on the comparison between the reference signal and what I get, then I can do a quality assessment. And we decided to use the L100 metric, B100 BD data from this YUV data. And I'll get more detail on that a bit later. So let's talk about the quality metrics. The first thing you can do is PSNR, a peak signal to noise ratio. That's what the industry uses. It's just the difference between the pixels, but the absolute values of PSNR do not directly correlate to perceived video qualities, but that's the simplest one, and we always start with PSNR. Then we have PSNR DE100, which is PSNR of the mean absolute delta E 2000 metric, referred to 100 nit luminance. There's a lot of literature showing that this is a good measure to use. By a good measure, I mean favorably matches with just subjective evaluation. And another one is PSNR L100, which is basically computed delta E 2000, but they just use the L component of that. Also compares very favorably in terms of matching subjective tests to the quality. So that's my point here. They correlate well.
And that's one of the important things is when a lot of people use PSNR, it's great for objective measurements, but it doesn't really reflect that well with what the human vision sees. For instance, something that should look better by its PSNR value, we could show side by side that it visibly looks poorer. These other two measurements here, the delta E 2000 measurements, these two other ones here, much more closely match the subjective results. We know what the human vision sees.
Yes. Okay. And the other thing we did is BD rate. Last year we didn't use that. This year we're going to use the BD rate, which is essentially an industry standard for computing either bitrate improvement for the same PSNR or PSNR improvement for the same bitrate. This is something that was proposed by Bjørntegard in one of the standards committees, and it is basically high. That's what industry is using today. So how do you do that? You plot PSNR versus log of the bit rate. You fit a curve to that. You calculate the area between the curves, and then you use that to derive the average PSNR. I know that I went too fast on that. Let me use an example. And these two curves I shamelessly copied from the Bjørntegard paper, so that is in there as well. So let's say you get two curves like that. Situation one and situation two, if you will, have bitrate and you have PSNR, whatever the PSNR measure you're using, right? You can either look at that way, a bitrate increase if you fix the PSNR, and of course then you average between the area, or you can do this, which is a PSNR increase. That, in a nutshell, is the BD rate computation, and that's what we use this year for this paper. So test procedure, and I put the paths over here. You take a baseline reading of the quality metric, use path 3. This needs to be done only one, and then you select the target bit rate. You run the PAT1 signal. And remember, I have put a little cheat sheet there where the PAT1 is the native HDR, and compute the quality metrics. That was a lot of work. Then run the PAT2, compute the quality metrics. That's again a lot of work. And then you repeat that for other values of BR. So you get that PSNR curve that I showed before. And then you do the BD rate computation. Here's my test sequences. I have 3 test sequences. 2 are from last year, 1 is new. Sequence 1 base jump is a 50 frame per second. The sequence 2 is baseball is 5994. And sequence 3 is a zombie sequence at 24. And the little boxes give you the sizes and resolutions and everything of the sequences. Okay, so let's take a look at the sequences. I have them. I'm going to play them for you. They are short, 12-second sequences.
As I wanted to point out before, again, just make sure we again realize that as the sequence is playing, that the SDR version of this is in the Ultra HD color space, and it's 10 bits. So it's not backwards compatible SDR that you can do on an existing non-HDR monitor.
All right. Yeah, it's not in that sense. So my second sequence is baseball sequence, and the third one is a well-known zombie sequence. I have no idea why this is called the zombie sequence, because there's no zombies in it. Maybe later. I'm just having commentaries so you don't get bored. Okay, PAT3 quality metric. So this is no encoding. You just go SL-HDR1 in and out. So what this table gives you is the loss you have by using SL-HDR1. So this, and you can also see this as a upper bound of what you can do with compression, because this is what happens if you don't do compression at all. So let's look at the test results. We'll start with HDR264, and I'm really proud of myself with those animated plots. I put the sequence names on the side so you don't forget what they are. So this is the PSNR versus bitrate, and you notice there's not log. I just do log for the BD rate, the baseball, and then SL with the PQ10. So you see the SL-HDR is higher, so you can expect a bit rate improvement here. The baseball sequence is right here, the SL-HDR here, and then almost the same for PQ10. And the zombie sequence is actually up there, SL-HDR first, and then the PQ10. They are very close. So L100 results, the other measure. So let's start with the base jump. It gives us that. And it's better than just PQ10. So again, we can expect a bit rate improvement here. Now the baseball sequence is over here with the other one, the PQ at a little bit lower. So we can just expect an improvement. And you can see here the zombie sequence and a big improvement over PQ10. 264 test results, basically the same thing. Now base jump, and you see it's basically one on top of each other, and in this case the PQ10 is a little bit better. Baseball down over there, again almost on top of each other. And then the zombie sequence, and again, almost on top of each other. L100, you're going to see a bigger difference. So SL-HDR1 for the first sequence, base jump. PQ10, you see a clear improvement, right? It's higher. Baseball sequence, you see a big improvement on this one. And then the zombie is over here, and you also see a big improvement. So you can expect a big change in bit rate. And once you crunch all the numbers, you get this on the BD rates. In this table, negative numbers means you can use less bit rate if you go SL-HDR1 and back. The only case where you don't get this advantages HEVC on the E100, but you saw that the curves are pretty closer, pretty on top of each other. So that is the advantage we're looking for, and we actually measure them again. Matthew.
Right. So this is where these results seem really, really odd to those of us that are in the industry on this, because what this is basically implying, because we're talking about comparing encoder entropy here. So again, the example encoders that we use here would apply to the other encoders as well. It's not, this is really about looking at the standards. The results are basically stating, as in most cases, as Ciro had just said, that you get better compression efficiency if you take the original HDR, convert it to SDR using SL-HDR1, compress it, the SDR, and then use the enhancement layer for the metadata that contains the HDR information, and then decode it at the other end versus just encoding the native HDR and decoding it, the compression efficiency. In other words, what the bit rate will be for the same perceived picture quality is actually better by converting it back to SDR. So that's what causes me to scratch my head on this, because assuming these results, of course, I have no doubt with my good friend Ciro, these results are correct. It's something that we'd want to take back to the the standards committee and say, hey, wait a minute, you're supposed to have the most efficient way of encoding, and here's something that's not part of the standard that is showing it gets better coding efficiency than the encoding itself if it was native HDR. So this is why it blows my world and other people are looking at coding entropy. This just doesn't seem to be possible, but yet that's what the results are.
Yeah, over multiple papers, multiple people finding this. It's probably because you could go back and tweak the encoder. You know, for example, for HEVC, there's a value called chroma QP offset, that if you mess with that, you get better performance there.
So hopefully that's it, because that's interesting. Now, we only have a few minutes left, so I'm going to let you do your thing, Ciro, because I don't want us to run out. Okay.
So metadata bitrate, we are adding metadata for the SL-HDR1. So there is an increase in bitrate there, but maximum size of the same message is about 61 bytes. So the upper bound is about 24 or 30 kilobit per second. It's negligible on that one. So conclusions, the impact depends on content quality metric. There's some indication that using metrics aligned with perceived quality for some content, lower bitrate can be used. More improvements in AVC are more marked in HEVC, and there's a 2017 paper that reported similar results with different metrics equipment. And I had these guys, I have access to these guys, I had them review this paper as well. So why are we talking about this again? So didn't talk about it in VidTrans 2020. We had a similar presentation, but we use now more advanced quality measures that better correlate with video quality, and we switched to BD rate. And we still found, and I'll be frank, we screwed up in one of the sequences. It was frame rate converted and was misconfiguration. So but that's the one where SL-HDR1 went way worse. Okay, we found problems with that. So I'm grateful to the organizers. They let me come here and set the record straight. So finished. Thank you for my wingman. And any questions?
Hey, good job, guys. Thank you very much. That was excellent.